also affiliated to equation experts. Yeah, so in this course, this one is an advanced physics. So I just want to make a quick presentation on vectors. Just a brief introduction to Newtonian mechanics. Newtonian mechanics uses Newton laws to solve mathematical problems or rather physics problems. So in this course, it's an advanced course. It is the whole itself, it is called classical physics. It is a physics on its own, classical physics. So in this course, our main problems we use to solve them using calculus. So this course, it is very crucial for those who want to further their studies to physics. Yeah, so this course began with the Galilean. So the same Newtonian mechanics that you learn in introductory physics, that's the same mechanics, but in this course it is advanced. That's the reason it is called advanced physics. Yeah. So I just want to make a quick presentation. So in this course we derive formulas. That is what we do. So those formulas that you use in introductory physics, we derive them from Newtonian mechanics. Like those, one of them is kinematics equation. So you can derive those formulas from Newton laws or Newtonian mechanics. So as we proceed, so just a brief introduction. Vectors are just quantities that have both magnitude and direction. And I believe you learned this at secondary, at grade 1, even at tertiary level, you've learned that. And you continue learning these quantities. So these quantities have both magnitude and direction. So because it has magnitude and direction, it means even their sign can be changing because it is a vector. And we want to say a vector can be a negative or positive, but a scalar mostly they are positive. Like you can't have a negative term, you can't have a negative mass, Yeah, so that is a scalar quantity. It doesn't have direction, it only has a magnitude. Because direction determines, a sign determines the direction of a quantity. So if it is negative, you know to say it is in the negative x-axis. If it is positive, it is in the positive x-axis. So even the motion, the laws of motion, they comply to those laws. So that's a mathematical way of explaining vectors. So what you're going to do here is just do a brief explanation on these same vectors. So an example of vectors, it is the first one is displacement. Displacement is one of the vector. The other one, it is what? Velocity. The other one is acceleration. I don't know if this is a correct spelling. Acceleration. Yeah. So displacement is just a distance that has direction. So distance is different from displacement. Distance has only size, not direction. So that means a distance can only be a positive value, but displacement can be negative because it has direction, and we say that direction can be determined using the signs or the operators, which is a negative or a positive. A negative shows it is in the negative x-axis, a positive shows that it is in the positive x-axis. So those are one of the concepts that differentiates distance from displacement. So distance can only be positive, displacement can be negative or positive, because those are what determines the direction. Same applies to velocity. Velocity can be negative or positive, which shows the direction of that quantity. Acceleration can be positive or negative, all that. Now, how can we show the displacement mathematically? So this is what we want to do. So displacement, if we are talking about the change in displacement using a delta, so this displacement can be changing from final to initial. So we can use delta to represent this change in displacement. So as I said, I am introducing you to Newtonian ways of driving and solving problems. So basically this course uses calculus to solve problems. So instead of us using small delta, which is x, we'll let this to be equal to dx. This is calculus wise, you know what dx is. So that's what I want to do here. So instead of us, so you can write this dx is equal to change this minus that. So with that in mind, we can try to, because that is displacement. Now what is velocity? Velocity is just when displacement is changing with time. That is what we call velocity. So the change in displacement with time is what you call velocity, or the rate at which displacement is changing. So you can define it in any of those ways. So if time is changing, then we can say, we can write it, so we can call this as equation 1. Then if now displacement is changing, so even the time, this is how we are going to denote it. So this, the right hand side has to balance as well. So this is what we are going to have. We are going to have t final minus t initial. Yes. So what we can do here is, because we are now talking about the change, the change from initial to final with respect to time, and that is velocity itself. So we can say we can say this is equal to what? A. I mean not A but V. We're talking about velocity, which is actually my name. So we're having V. So let us just write this in a proper manner. So this will be V is equal to dx dt. So you can call this as your equation 2. So this is how we denote velocity calculus with. Now what about acceleration? What is acceleration? So acceleration is the rate at which the velocity is changing. So the rate at which velocity is changing is what you call acceleration. Now sorry, let me do this. I've made a mistake. In short, I'm just making correction. So this is changing, final changing. So changing this is what we are saying here, not just like that. So things have to be balancing here. things have to be what? Balancing minus V naught is equal to that. So this is what we have. Now what happens if at all this velocity is changing with time? What can happen? What can we get? So if velocity is changing, then it means we are dividing this by what? T final minus T this. Then this will just be D over dt, multiply this thing. But you know to say dx dt is equal to what? Velocity v. So we can get that. So if we call this as your equation A, we can take, so what you do, we are taking equation A into equation 2. So what are we going to get if we do this? So we're going to, this is what you're going to get here. So because that one is going to be acceleration, so acceleration is actually equal to dv dt. So that's what we're getting. So you can also, because acceleration, we are talking about the change. Yeah, so since acceleration is changing, so you can also denote this in this way. If at all you are, so you can also write this as, yeah, it is changing from this to that if you want. But all you know what you want is what? Acceleration. So this acceleration can be changing that much. In case it continues changing, at every instant it is changing, how can you find the average acceleration? Yeah, so acceleration will be changing that much. So, but my interest is to just have this part here. Okay. So this is we can call this as our equation what? 3. Now, yeah, so those are one of the vectors that we need to know, and they are very, very important. So what if you are taught to find displacement, doing the vice versa? What can we get from, okay, so like from equation or in short, if you are taught to find the velocity as well as the position, so what can we get? So from equation 3, if we are to cross multiply there, we get A dt is equal to dv. So this is what we are getting from equation 3, and you can write this equation as dv being equal to A dt. Now if we integrate here, because they are using Newton laws, which uses calculus, when we integrate this, what do we get? You're going to get v, which is actually velocity. Then here we're going to get a t plus we can call this as c1. So we can call this as equation what? So from what we've been having, so this is equation 4. So you know, this velocity, the whole system equation is changing with respect to time. So this is like that, C1. So we can do this. Then instead of writing this as equation 1, we can write this as equation 4. So you can write it in that manner. So now, from this equation, if we consider an object that started from rest, so at rest time was equal to what? 0. So if we substitute this, we are going to find that from equation 4, we are taking t to be equal to 0. We're going to get, if we substitute this, the v is 0, and this is actually, this is 0 plus c1. So you can see that the v is equal to c1, but taking into consideration that at t is equal to 0, we have initial velocity, so you can see v naught is equal to c1 is equal to this, which is that. Or instead of me confusing you, let me do this. What I mean is the v is after substituting, this is what you're getting. So this part. So if we call this as your equation B. So if that's your equation, now taking equation B into equation, so what is our equation here? Because we want to eliminate the constant to equation 4, so that is equation 4. So we get what? So if we substitute there, so we're going to have Vt being equal to At plus V naught. And I believe you know this equation, because you've been writing this equation, you write it in this way. So this is one of the equation under linear motion, an object that is moving in a straight line. So this is an equation that you know. So you can call this as your equation 5. So this is an equation. This is velocity. If you're taught to find velocity from acceleration, the one that we were driving. So this acceleration, which is equation 3, if you are taught to find this velocity from this equation, then what about the displacement from this same equation? So we're going to utilize equation 5, which we've found there. We make use of that beautiful equation. That's a beautiful equation. You know, this beautiful equation, you have to take care of those, because without those you wouldn't have this technology that you are seeing, having these phones, having advanced military weapons. Without these equations are very, very important. So let's make use of them. Even in our daily lives, you have to be applying this equation. In case you are in an aeroplane, then that aeroplane maybe at some point you have a breakdown in the sky. How can you utilize these equations? Assuming that you're a physicist, how can you utilize these equations? Can't you just use them? to calculate the distance at which the plane is going to crash at the ground, so that rather not distance but time, so that you communicate with people who are able to save you. How can you use this? Because your airplane can actually determine the distance. So that means you can have distance, gravity is there. If you are using due to gravity, then you are able to calculate the time at which it is going to reach the ground. Yeah. So from equation 5, so we are saying that from equation 5, we have Pt is equal to At then V naught. Now, since you know to say V, we said V is equal to what? Dx dt. So this equation C, this is what we say. So this is what we said. So equation C, you can call this one as equation C. You can call this as equation C. So taking into consideration of taking equation C into equation 5, because this is equation 5 that we are from driving. So if we do that, what are we going to get? So we're going to have something like dx dt being equal to At plus V naught. So we can erase this part. So let's make use of this beautiful equation to save people. Imagine saving those people in an airplane with those equations. You'll be given a lot of money. So those are one of the applications of physics. Because we are trying to understand how we can apply this physics. As you go further with this course, you also discuss some the air resistance. We won't be, assuming to say it's negligible. No. We'll make use of air resistance so that you are able to calculate the time that that an airplane is going to take to crash. So you are able to save people from those equations, because that airplane will have some air resistance due to the surface it has and the mass itself, because mass will also contribute to the force of gravity, because the larger the mass, the larger the force of gravity. The larger the mass, the larger the force of gravity, because we are now talking about the weight. It is putting you down. So that's the reason if you want to experiment to say, this object can fall at the same time, unless in a situation whereby you're talking about the vacuum, but where there is air resistance, they are going to fall at a different rate due to the masses. Okay, so from this equation, we can actually, here what we can do this. Let's multiply this by the inverse of t, which is actually dt. So this is actually dt. So if we do this will cancel with that, but then here, what are we going to get? I'm going to get dx being equal to a dt dt plus v naught dt. Then from here, you can integrate these guys. So let me do it. So we can integrate these guys. We can integrate even there. So what are we going to get? So if we integrate this, you're going to get x. Then this because I know you have some mathematical concepts. How do you integrate? This is n plus 1 over n plus 1, where n can take a value 0, 1, 2, any natural number that you're talking about there. So applying this principle where n is a power of t, so you add plus 1 there. So what are you going to get here? You're going to get a t squared over 2 plus, and this will be v naught t plus, you can go c2 because you're going to have a constant there. These are just some of the mathematical theorems under calculus. So we can write this properly. So this is actually a t squared over 2 plus v naught t plus c2. Because you are still talking about an object that started from rest, and at rest you know to say t is equal to 0. So it started. So if we substitute this, so let me erase this. So as I was saying, you can say of people using these equations. So air resistance has also effect to this object that fall. It's not always negligible. So at secondary you are neglecting this. Even at the first year I see people neglecting air resistance, but as you go further with physics, you stop neglecting this. Air resistance also plays a crucial role to the object that falls. Okay. Okay. So taking t to be equal to 0, taking t is equal to being equal to 0. So this is our equation 6. So this is our equation 6. We are taking t to be equal to 0. So if we substitute this, what are we going to have? We're going to have x is 0 of a 0 over 2 plus v naught t, or 0 here, plus c2. So what you're going to have here is this is equal to, this will be 0, 0, then this will be c2. But taking note that you're going to have initial displacement that we derive in our first equation. So we can conclude here and say this is equal to x naught, which is actually a displacement. So we can call this equation D. We can call this as equation D. So okay, now taking equation D into equation 6. So this is what you're going to get. So from equation 6, if we put x naught there, we're going to have x go to a t squared over 2 plus v naught t plus x naught. So these equations are very, very important, guys. So they save people. People shouldn't be dying, especially if you are building an airplane, especially these engineers. Some of engineers that memorize theories are the ones that makes the planes to crash. So let's avoid those memorizing, because it has a huge impact in the technology sector. Very huge impact. Okay. So from this equation, we have this equation, but you can write this as x naught plus v naught t plus 1 plus 1 over 2 a t squared. Now, you know this equation. You've been seeing this equation, so you can write this as, sometimes you can write this as this, because all these are changing with respect to time, so you can also write them like this, because you already know at squared. So if you say, because you're considering this to, so x naught to be initial, then 1 over 2 a t squared. So I know you've been seeing this beautiful equation, but you don't know where it came from. But me, I've shown you. Imagine, the same thing that I've been, the same story whereby you are in the sky. Now you've forgotten this equation. Now you know the plane is about to crash. There's a breakdown in the sky. What can you do? You drive this same equation from where we started there. Then after finding the equation, you try it to calculate the time it will take for a plane to crash. Now, you can take s to be equal to, because we are talking about the change. We talked about the change in displacement, or rather, I'll just take it as, because we said the displacement can change. So the change in the displacement in this manner, we can use it. You can use this equation, you substitute it there. So if this is equation A, then taking that equation, so we are going to have S being equal to plus 1 over 2. This is acceleration. So this is at squared. You know this equation. You've been playing with this equation. Yeah. So this is what you need to know. And there are other equations that you can derive, even the kinetic energy itself that you've been using. You don't know where it came from. The same forces, momentum. You can derive those equations. So just follow my channel, because it is going to encourage me to make more videos. Follow my channel on YouTube, as well as on Facebook, Dr. Velocity, the nuclear physicist. You can also follow Equation Experts, because I'm part of that group. Yeah, thank you so much.